Hello everyone, welcome to EKM Analytics, where we empower data-driven decisions. My name is Esdras Koome. Today, I'll talk about multiple linear regression model in R software. Sit back and enjoy as we learn together. So, what is multiple linear regression? Multiple linear regression is a statistical method used to model the relationship between one dependent variable, also called the response variable, and two or more independent variables, also known as predictors or explanatory variables. The goal of multiple linear regression is to predict the value of the dependent variable based on the values of independent variables. Note here that the difference here is that from simple linear regression, we had one independent variable, but here now we have two or more independent variables. Hence the equation y is equals to beta naught plus beta 1 x1 plus beta 2 x2 all the way to beta n xn plus the epsilon, where y is the dependent variable, x1, x2 all the way to xn are the dependent variables, beta naught is the intercept, which indicates the value of y when the dependent variables are equal to 0. Beta 1, beta 2 all the way to beta n are the coefficients for each predictor, which present unit change in y when either of the dependent variables have a unit change, and the epsilon is the error term. For instance, assume that you want to predict the number of customers you'll have in future after conducting several public awareness campaigns and commodity campaigns. Therefore, you track this information and have it on monthly basis. And therefore, here we notice that the number of customers that will be registered will be our dependent variable. And then we shall have two independent variables, that is the public awareness campaigns and the commodity awareness campaigns also. Therefore, our equation becomes customer registered is equals to beta naught plus beta 1 times the public awareness campaigns plus beta 2 times the commodity awareness campaigns plus the epsilon. To ensure valid result in multiple linear regression, there are assumptions that must be met. 1. Linearity. The relationship between the dependent and independent variables should be linear. This means that the change in independent variable is proportional to the change in the independent variables. Number 2. Independence of errors. Observations should be independent of each other, meaning there should be no correlations between the residues. Number 3, we have homoscedasticity. The residues should have constant variance across all levels of the independent variables. This is also known as equivariance or homoscedasticity. Number 4, we have normality of residues. The residues, into bracket errors, should be normally distributed. This assumption ensures valid hypothesis testing for the regression coefficients. Number 5, we have no multicollinearity. Independent variables should not be highly correlated with each other. Multicollinearity can inflate the standard errors of the coefficients, making it difficult to access the effect of each predictor. Now, to check whether these conditions have been met, we use what we call diagnostic plots. Our first diagnostic plot is the residues versus the fitted. This plot shows the residues, which are the errors, versus the fitted values. Ideally, there should be no clear pattern, a random scatter, in these plots. A slight curve here will suggest some potential nonlinearity. Our second diagnostic plot is the QQ plot. The QQ plot compares the distribution of residues to a normal distribution. The point should follow a straight line, hence suggesting that the residues are approximately normally distributed. Our third diagnostic plot is the scale location plot. This plot shows the square root of standardized residues versus the fitted values. It's used to check for homoscedasticity. A horizontal line with equal spread points is ideal, else we shall rule out heteroscedasticity. Our last and fourth diagnostic plot is the residues versus the leverage. This plot identifies influential data points, observations with high leverage. There is a Cook's distance line that indicates whether or not the points seem to be far below this line, hence suggesting if or not there is existence of any single observation which is unduly influencing the model. If nonlinearity or heteroscedasticity is a concern, you could consider transforming the variables or using a different model that better captures the relationship between x and y. You could also check on any outliers or influential points that might be affecting the results. That is the end of part 1. See you in part 2, where we shall be conducting the coding in R.